Hey students, today I'm making a little tutorial on how to find all the nth roots of both real and complex numbers. I'll start off by showing you how you can find all the nth roots of a real number, and then I'll do another video on the differences when we're starting with a complex number and trying to find all the nth roots of that as well. So up on the screen I have a little tutorial that I made on how to do it. Essentially, what we're going to be doing is changing our real or complex number into a complex number in polar form. After it's in polar form, we can quite simply take the nth root to find one of the nth roots of that number, basically by using, it's called DeMoivre's Theorem, which technically only works for integer values of exponents, but it actually will work to find the primary it'll help us find the first one, and after that is a simple extension of DeMoivre's theorem called the Nth Root Theorem, which essentially says that if you take that first result and repeatedly add either 2 pi over n or 360 over n, you will get the rest of them. So I'm making this video because the formula makes it look really complicated, but it's actually fairly simple when you get the general idea. So let's start off with a first example. Let's say we wanted to find all the third roots of the number 125. So if we're looking at the number 125, well, probably just about as any of you would know, if we took the third root of 125 and with the radical notation, where taking the nth root of 125/3, you probably would all know this is going to be 5, or most of you would know, because 5 to the third power makes 125, and that's how roots work. So but again, this is only one of the nth roots of 125. There's actually 2 more, and actually any number, if you're looking for, say, the cube roots or 4th or 5th roots, there's always that many roots of that number. So 5th roots will have 5, 6th roots will have 6, and so on and so forth. So actually for 125, there's actually 2 other numbers besides 5 that, when raised to the third power, make 125. So there are more cube roots out there, and this is how we find them, essentially. So going back to the step-by-step to help try to make this as simple as possible, the first step is to write the number as a complex number in polar form. So 125, going back to, say, we're trying to find the cube roots 125, we're not going to use the cube root notation, like the radical notation. But if we write this number first as a complex number, well, 125 is just as a real number. It has no complex component. So how we'd write it as a complex number would be 125 plus 0i, as probably most of you would know as well. And from here, then we want to write this in polar form. So polar form is an alternate way of writing any complex number. Basically, instead of using the rectangular coordinates of the complex number in the complex plane, we're looking for the r cosine plus I sine theta, as it's called. So anyways, if I create a little sketch, let's try to illustrate how polar form works really quickly if you don't already know. But on the complex plane, we have a real and we have an imaginary axis, where the real portion of our number in this case is 125, often called a, is graphed in the real direction, where any imaginary component is graphed in the y direction, or along the imaginary axis. So if we're trying to graph this number, we would essentially treat it like it was an xy coordinate and count 125 along the real axis and 0 along the imaginary. So in this case, if we're looking at the coordinate 125, 0, well, of course, that would be right 125 along the real axis and up and down 0. So with any real number, we would just count our way over 125, to the right of the axis, and way over there would be this number, a real number. So basically, what's nice about this is every real number in the complex plane is on the real axis. And so in polar form, the polar form of this number, instead of utilizing the x and y coordinates, we're looking for the r and theta coordinates, because that's how polar form works. Well, in this case, r is the distance from the origin, theta being the angle in which our point is taking from the standard position at along the positive x-axis. So again, with any real number, what's kind of convenient about it is that the distance from the origin is exactly 125, or if you use Pythagorean theorem, or the distance formula for this point. Of course, since we're not moving up or down, the distance is directly the same we counted out to begin with, 125. So r, if we're looking at the polar form of a complex number, r would be 125, and theta, well, again, we're on the x-axis in the positive direction, so this would form an angle of 0 from the beginning, just like you do with trigonometry, with your trigonometric functions. You know, we would look at what angle we're at, but with this point, we are not at any angle, we're along the positive x-axis, which is the beginning, by definition, of any angle in the polar form. So anyways, essentially what this means is our r, which is sometimes called the modulus, would be 125, and our theta, called the argument, is 0. I'm going to do it in degree mode. I like to do it in degree mode because I think it's a little simpler, and when we're adding, when we're finding all the roots, we need to do fractions of values, and if you use radian mode, then you have to take fractions of 2 pi, and it just makes it a little bit more annoying to find, to look at all the different positions, and I think degrees are a little bit easier for the common person to understand, so we're just going to do it in degree mode. So anyways, that complex number 125 plus 0i would be written as r times cosine plus I sine theta, again, by definition of how polar form of complex numbers work. So we'd have r 125 times cosine of theta plus I times the sine of theta. In this case, basically I figured out it was very easy to find these values for this number because it's at an angle of 0. But if you're dealing with other numbers, complex numbers that are elsewhere in the plane, it takes a little bit more work to find those, and that's what we'll do in the next video. But for the sake of this problem, as we do in class, and some people will write polar form of complex numbers in the shorthand version, but instead of writing out cosine plus I sine theta, I said it's okay in my class to write it like this, CIS of 0, which is just a shorthanded way of writing it. There's an actually faster way to write it, which is using Euler's formula, which is something we don't get to in precalculus, so I'm going to save that. But essentially you could also write this as e to the I theta for reasons that you'll talk about if you ever take a course on complex analysis, but we don't quite get to it in precalculus. It's kind of nifty, but this shorthand version is essentially equivalent to that. And anyways, what it means is cosine plus I sine theta, and it's just a way that we don't have to write out that quite as much, you know, cosine I sine theta. If we have to write this over and over again, you know, it just takes a lot of writing. So shorthand is nice. So anyways, that's our number in polar form. Let me just go ahead and circle this. So that's step 1 is completed. My real number 125 is written as a complex number, and any real number, as I mentioned in class, you can just stick on that CIS 0 to it, and that will turn that any real number into a number in polar form. So real numbers are really easy to write in polar form because their argument is always going to be 0, or technically 180, but it just makes it really fast and easy. So back to the second step. So what do we do next? Find one root by raising the complex number to the 1 over n power, where n is the root's index. And it says use DeMoivre's theorem to simplify. So before we start doing that, just talk a little bit about DeMoivre's theorem, which is this theorem here on top, as you see it in your textbook. So it says if z equal to r cosine plus I sine theta, then for any integer n, z raised to the nth power is equal to r raised to the nth power times the quantity cosine n times theta plus I sine n times theta. So if I could put that into words simply, if our complex number is written in polar form and we want to raise that to any power, basically what we do is we take the modulus r, raise that to the nth power, and we take our argument theta and we multiply that by n instead of raising it to the nth power. So it's a really handy shortcut that makes finding powers really easy. Technically, DeMoivre's theorem only works for whole integer values, so when we're doing it, we're kind of doing something we're not technically allowed to do. But it really does work for any power, but it only will, the problem with DeMoivre's theorem is when you use it, it only will give you 1. So the theorem right below it called the nth root of complex numbers, or sometimes also called the nth root theorem or DeMoivre's formula, will find all the other ones that DeMoivre's theorem, as it's stated up here kind of in a simplistic way, will not find. So instead, I mean, this way is totally fine if you get how the formula, what it means, but I find that my students have difficulty understanding the formula, so that's what this tutorial is all for, is kind of trying to simplify this process a little bit and make a little more sense of it but essentially kind of what this formula, the implications of this formula is that when you find one complex number, one complex root of a number, all the other ones are actually evenly spaced about 360 degrees about the complex plane based on the nth root. So if you have three of them, they're all going to be separated out evenly. And what kind of happens is when you graph them, they look kind of like evenly spaced spokes, like a hubcap, for example. And we'll try to do a little graph at the end of the complex numbers. But essentially, it's very periodic in nature. All the roots are spaced evenly. It's kind of interesting. But okay, back to let's do it for this example. So what we're going to do is we want to find the nth roots of 125. So again, if you're kind of lost track of the problem we're doing, we're trying to find all three cube roots of 125. So 5 was one of them. What are the other two? Essentially what we're getting at. So if we want to find the nth roots, well, we would take the nth, we would take the nth power, and the nth root, raise it to the cube root, essentially, or that's the same as raising it to the 1/3 power, because remember the cube root is the same as if we raised it to the 1/3 power. So essentially, if we take our number 125 CIS 0 and we want to find the cube roots of that number, we take it, raise it to the 1/3 power, so we'd have 125 times CIS 0, and this would be all to the 1/3 power. And this is kind of the idea. We want to find the cube roots. And so by DeMoivre's theorem or DeMoivre's formula, what happens is the 1/3 goes to the radius r directly. So we would get 125 to the 1/3 power. And what happens to the power with CIS, if you take CIS or cosine plus I sine theta and raise that to the 1/3, what happens is the 1/3 actually multiplies to the 0. And if you're wondering why does it multiply to the argument and not do something else, it's actually a very an interesting way that complex numbers multiply on the complex plane. So how they figured this out is mathematicians, I guess DeMoivre probably was one of the first people to figure it out. I'm not exactly sure, but as you try multiplying numbers in the complex plane, when you multiply two of them, the radiuses multiply normally, and the angles are actually have an additive effect. So like if you multiply two complex numbers with an angle of 30 and an angle of 45, after you multiply them, the resulting angle would be 30 plus 45 or 75 degrees, instead of being kind of a multiplied effect. And that product is kind of called the product of two complex numbers in polar form. It's very easy to show using sum identities for sine and cosine. So it's actually not that hard to see that it's true if you look at the proof. But again, we already did all that in class. This is not the topic of this one. Anyways, so 1/3, the point is 1/3 multiplies to 0. So we get CIS of 0 times 1/3, which is just 0. And so we'd be left with our first nth root is, 125 to the 1/3 power times CIS 0. So that would be, 125 to the 1/3 power is what we kind of did earlier. Well, it's the cube root of 125, so we get 5 CIS 0. And so at this point, you might be like, well, what's the point of doing this? We already knew that 5 was an nth root. And so essentially, yes, we find out one of the nth roots is 5 CIS 0, but essentially kind of the way this is easier is that we can find the rest of them by doing step 3. So find the other roots by using the Nth Root Theorem. And again, that's that theorem that was a little bit complicated as it is in the textbook, but basically the shortcut that I like to teach in my class is you take that first one, you repeatedly add 360 divided by n, and that will generate all the rest of the roots. Then that's as easy as it is, actually. So we're going to repeatedly add 360 over n, where n is the index of your root. In this case, we're finding the cube root, so n is 3, and there should be 3 of them. So we're going to be repeatedly adding 360 over 3, or 360 divided by 3 is 120. So we repeatedly add 120, and that will find the other, in this case, 2 other roots. And if you're doing it in Radian mode, say you like Radian mode, or like your online homework only will work with radians sometimes. So you, instead of doing this all in degrees, just start off in radians, and instead of adding 120 degrees, add 2 pi over 3 repeatedly instead. So it's a little bit more of a nuisance to do in radian mode, but that is what it is. So anyways, this is our first root right here. And so if we want to find the other 2, we take the first one and we repeatedly add 360 over n. So add 360 over 3 because we're finding the third roots, the 3 third roots. So we're adding 360 divided by 3, or 120. So if we add 120 to the argument, that would be 5 CIS 120. Again, we take the angle in there and add, that's where we're going to add that to, and this will find the secondary root. And then do it once more, and we find the third roots. We get 5 CIS of 240. And then now this will be all 3 of our cube roots of the number 125. So it's pretty easy. And again, so it's actually very simple to see why this works. But remember, if something is a cube root, that means if you cube it, what should happen is it should get back to 125. So basically, all 3 of these numbers, if we cube all of these, we should get 125. So again, using DeMoivre's theorem, we could easily cube these numbers. If we cube the first one, we would get 5 cubed is 125, and 0 times 3 is 0. So we get 125 CIS 0, which again is 125. If we take 5 CIS 120 and we cube that, we would get, well, 5 cubed is 125. CIS 120 cubed, well, 3 would multiply to 120, so we would get 125 CIS 360. And as you guys should be aware, 360 degrees is coterminal with 0 degrees, so we'd actually get 125 CIS 360, which is the same as 125 CIS 0, which is, again, just 125. So cubing this will also net 125, and also, as you can imagine, cubing this one should also net 125, because if we cube this using DeMoivre's theorem, we get 5 cubed is 125, CIS 240 to the third power, well, 240 we'd multiply by 3, so that would give us 720, which again is the same position as 360 and 0, so again we'd be at this 125 CIS 0 would be coterminal with 720, and so that would also be exactly the same, 125. So in essence, that's how it works. And you can actually continue to add 120 degrees over and over again. But as you'll see, if you keep adding 120 degrees beyond 240, you're going to repeat yourself, because you're going to get 360 degrees, 480, 600. And those will all be the same, those same angles just repeated. I mean, they're not the same angle, but they're coterminal. They would have the same cosine plus I sine. So they're repetitive, and they give you the same results beyond. And so just do it until you find all of them. In this case, we're finding the cube root, so there should be 3. And so we found all of them. So what I want you to do a lot of times on the test is to write these in the normal rectangular form. So, we can do this pretty easily in polar form, but what numbers are these, as we normally look at complex numbers? So if we're trying to write them back kind of as a normal number, what would this get us? So that's what we're going to do next. We're going to take these 3 complex numbers, and we're going to turn them back into rectangular form. So our first root was 5 CIS 0. Our second was 5 CIS 120. And the third was 5 CIS 240 degrees. And so to turn it back, well, is actually really easy. You just expand CIS theta, which means cosine plus I sine. So if we want to turn these back into normal numbers, well, I already mentioned that CIS 0 is 1, is equal to 1, just the number 1. But, it kind of helps to see it expanded, but if we expand cosine plus I sine, we get cosine theta plus I times sine theta. So we expand this, and we get 5 cosine 0 plus I sine 0. And, well, what cosine of 0 is, at 0 degrees, cosine would be 1, and sine would be 0. So we get 5 times 1 plus 0I, because sine of 0 is 1, and cosine of 0 is 1, and sine of 0 is 0. So we get 1 plus I times 0, or just 5 times 1 plus 0I, which is 5 times 1, or 5. So, this is, again, going back to the first obvious cube root of 125, which is 5. So this one over here, these other two are those other two sort of mystery ones that, your calculator won't give you if you type in 125 to the 1/3 power. But if we take each of these, again, if we expand cosine plus I sine, it would be cosine of 120 plus sine of 120. And so I'll just go ahead and do it like this. I won't rewrite the whole thing, but first I'm going to be doing cosine of 120. So at 120 degrees, let me go ahead and pull up my unit circle here. So cosine of 120, just to review, is our x value at 120 degrees. So at 120 degrees, cosine would be negative 1/2, and sine would be rad 3/2. So cosine of 120, again, I'm going to do cosine plus I sine. So cosine's negative 1/2 plus I times sine is root 3/2. Again, simply expanding CIS 120. And then if we use the distributive property here, 5 times negative 1/2 is negative 5/2. And then 5 times positive I rad 3/2. Well, we could just write 5 rad 3/2, and then normally we write the I at the end, but we would get this result here. So this would be another one of the cube roots of 125. And the other one is actually going to be the conjugate of this, and we'll talk about that in a little second. But if we take CIS 240, expand that again, we would do cosine plus I sine. That's what the CIS, as we do it, stands for. So cosine of 240 is down here. Cosine of 240 is negative 1/2. Sine of 240 is negative root 3/2. So we get negative 1/2 plus I, and sine of 240 was negative rad 3/2. And again, basically the same math here. We could use the distributive property, and we get 5 times negative 1/2 is negative 5/2, and then 5 times negative rad 3/2 is negative 5 rad 3/2. And of course we have an I on that component because cosine plus I sine, we need to have that I. So there we have it. Basically these other two, these three numbers here are going to be the 3 cube roots of 125. And again, what that means is that if you take those three numbers and you cube them, it's 125. So obviously if you take 5 times 5 times 5, that's 125. But if you take these numbers and you multiply them repetitively 3 times together, it makes 125. And it doesn't really seem to make sense because these are kind of weird numbers. But if you just so happens that if you foil them out three times, when you multiply them all together, it actually also makes 125. And so if you're a little skeptical of this working, let's quickly check this out using our TI 83. So if I pull up my TI 83, basically if we take those three numbers and we cube them, we should get 125. Again, this is what a cube root of a number is. So we're going to take our results and make sure that when we cube it, it's 125. Well, that one's obvious. 5 times 5 times 5 is 125. Let's try the other ones. Negative 5/2 plus 5 rad 3/2 times I. Whoops, I is right there. So there's my second root. And what I'm claiming is that when you take this and you raise it to the 3rd power, that should give us 125. And some of you might be concerned because it looks like I'm dividing by 2i. But how our calculator works is if you type 5 rad 3 /2, that'll be 5 times rad 3 divided by 2. And then if you just put an I next to it, it'll be times, unless I put this in parentheses. So If I put this 2i in parentheses, my calculator will divide by 2i. But in this case, it multiplies by I. So if you're concerned about the order I wrote that in, this will be fine. But anyways, if we cube that kind of strange number, we get 125 also. So again, you could FOIL it by hand. It'd take you a little bit of work to see that will work out to be 125. But it would be a good exercise. And then lastly, if we take the other one, the conjugate of it. So let me pull up my previous answer. And I'm just going to change the sign in here to negative because the third root that we found was the same one as above, but with a minus sign in between. So if we check that one also makes 125 as well. And so that's all of them. That's all. Those three numbers are all going to be the cube roots of 125. So a fairly little, not very well understood topic, finding alternate roots of numbers, but I think it's pretty cool. And it's actually pretty easy if you use the little step-by-step guide. And if you want to look at that, you can rewind there and pause it and write it down if you want. But there we have it. So a couple last little things to talk about this. Just a few other little interesting things, like to connect this to polynomials and graphing as well. But another nice little thing to remember about the three roots of 125, or any real number in this case, is since they're evenly spaced about the complex plane, what that means is we can sort of visualize where those roots lie. If we look at 5 CIS 0, if we look at the first root right there, that would be at angle 0, so it would be along the positive x-axis, and it would be distance 5 away. So if we count out 1, 2, 3, 4, 5, our root's going to be right here in the complex plane. And if we did the same for the other roots, 5 CIS 120, that would be at an angle of 120 degrees, which would be approximately something like that at that angle. And we would count 5 away, however far that is, 1, 2, 3, 4, 5 away from the origin. We get that root over there. And then the third one at 240 degrees. 240 degrees is the angle down here. And again, if we count off 5 away, we get somewhere about there as well, whatever your scale of your axis is. But if we kind of connect each of these roots to the origin and look at them kind of in a polar graph, they form an evenly spaced sort of hubcap looking shape. It's always going to be very symmetric. In this case, the angle in between each of those is 120 degrees. Looks kind of like a sideways, Mercedes-Benz symbol or whatever peace sign or whatever sign kind of looks like that. But basically, all those angles are 120 degrees evenly spaced. So the higher of index on your root, so 4th roots, 5th roots, 6th roots, 7th roots of numbers you take, there's going to be more and more of them, and they're all going to have the same sort of trait. They're all going to be evenly spaced. So if you have 4 of them, they're going to be spaced about 90 degrees symmetry, 5 of them 72 degrees, 6 of them 60 degrees. Basically, if you want to know the symmetry of it, you just take 360, divide it by your n, and that's as simple as it is. You can find that's where all those roots are going to be, regardless. And again, this for real numbers, they're always starting at 0, so it's very symmetric. And the conjugate, both the complex conjugates will be together. If you're taking the nth roots of not a real number like a complex number, it's very similar. They're just starting not at 0, so the symmetry gets rotated a little bit. But again, one last little point about the conjugates is I mentioned that I knew that those two conjugate roots were going to be like those second and third roots will both be part of it, both be conjugates. And if you remember back to polynomials, if one complex root is ever a root of a polynomial with real coefficients, its conjugate must also be a root. That's a property that exists because in order for the polynomial to remain real, the imaginary components have to be canceled out. And then in this case, solving the cube roots of a number could be modeled using a polynomial, and actually we'll do that in just a second. And you can use sort of polynomial ideas to find these as well, but this process is much easier for solving complex roots of more, if you're finding more of them, because with polynomials, if you're trying to find like eighth roots of a number, you'd have to deal with a polynomial of degree 8 and then further and further. It becomes more difficult with polynomials. Then this process is much simpler for finding the other roots of those numbers. But again, when you're dealing with real numbers, complex conjugate should always be a part of it. And then the symmetry of adding 360 over n will always, the conjugate will always be a part of that. And if you do some examples, you'll run into that as well. So anyways, last little tidbit on this. Let's look at the polynomial solution method, kind of a different way of solving this type of problem, and just connect some of the ideas together. So, okay. So essentially we found all the cube roots of 125. That could be sort of the same thing as if we solve the polynomial x to the third power is equal to 125. Because, you know, if we're going to solve this polynomial, what we'd get would be what numbers are when cubed raised 125. So this polynomial is a synonymous problem, finding the cube roots of 125. So, you know, if we're, you know, going back to basic algebra, if we subtract 125 from one side, from both sides, and we try to factor this polynomial, if we can fully factor it, we can find all the roots. So similarly, we could do this. And you might recognize x cubed minus 125 is called the difference of cubes because both numbers are cubes. So this can actually be factored formulaically. And if you remember the formula, it goes like, if we call it a cubed minus b cubed, I think it works like a minus b times the quantity a squared minus a times b. So in this case, it would be plus 25x, and then it's either plus or minus b squared. I can't remember the formula exactly, but I do know that it will factor like this. And you can look up that factor. It's just called the difference of cubes factor formula or something. That should be pretty easy. But if we were to distribute this thing all out, we would get x cubed plus 5x squared plus 25x, then minus 5x squared, then minus 25x, and those both those inner products, all those will cancel, and then we'll be left with the last thing, negative 5 times 25 is minus 125. So we just have x cubed minus 125. So this does match the thing above it, and from here, well, the first term obviously has a solution of 5, because you know how we solve it from here is we set each factor equal to 0. So x minus 5 is 0 when x is equal to 5, and this thing is 0. Well, this would be a quadratic, x squared plus 5x plus 25. Of course, that's not 0 for any real number. If you try to use like a magic x or something to try and factor this, you can't actually factor this. So you might say it's a prime polynomial. But if you use the quadratic formula, and you know, as we already found, we found the 3 roots of this number already. So this polynomial actually does have 2 roots, and if you look at all your polynomial, the fundamental theorem of algebra is that any polynomial can be fully factored. So this thing actually does have 2 roots. They just happen to be complex. So we could always use the quadratic formula to find the roots of this bad boy. So we would get x is equal to negative b plus or minus square root of b squared, so b squared in this case is 25, minus 4 times a times c, so a would be 1 and c would be 25, so 4 times 1 times 25, 4 times 25 is 100, so we'd have minus 4 times a times c, which is 100, and then that would be all divided by 2, and if we simplify this a little bit, we would get minus 5 plus or minus the square root of negative 75 over 2, and we could simplify this. Some of you may already be realizing this is very similar to those other roots we got just a few minutes ago, but 75 is 25 times 3, so we could factor out the 25 and take the square root of the 25, which would be 5, so we have 5 rad 3, and with the square root of any negative number, we represent the negative as I, that I is the square root of minus 1. So if we split this all up, we get minus 5 plus or minus the square root of, 5 times the square root of 3 times I, all divided by 2. And looks like we're running out of space here. Let's bring that up just a little bit. So we would get 5 plus or minus 5 root 3 times I all over 2. Or if we split this up, we would get negative 5 halves plus or minus 5 root 3 over 2 times I. And those are exactly those two conjugate answers, the conjugate pairs of roots that we found before. And so some of you might be thinking, well, it was kind of easier to find my solutions. X is equal to 5 and X is equal to negative 5 halves plus or minus 5 right there over 2I. Doing it this way, which is true for this problem. But as I mentioned before, if we're dealing with higher powers beyond cube roots like 4th, 5th, 6th, 7th, 50th roots, finding all of those with a polynomial would be a nightmare because factoring, the higher your degree, the more difficult it becomes to factor. So again, it's very valuable to do it using polar forms and other roots as well. So that's kind of the main idea. So just sort of like if I wanted to explain another example off the top of my head, say we're trying to find the 4 fourth roots of 16. And of course 2 and minus 2, if you square those, you get 16, or I mean raise them to the 4th power, you get 16. But there's 2 more fourth roots, again because there should be 4 fourth roots. And if you start off with 16 CIS 0, so number in polar form, and we use DeMoivre's theorem, raise it to the 1/4 power, we get 16 to the 1/4, which is 2 CIS 0 times 1/4 is 0. So we get 2 CIS 0. We repeatedly add 360 over n. In that case, n would have been 4. So we repeatedly add 360 divided by 4, which is 90. So we take 2 CIS 0, add 90, 2 CIS 90, add 90 again, 180, and then 2 CIS 270. We get 4 roots, which would be, let's see, so 2 CIS 0, 2 CIS 90, 2 CIS 180, and 2 CIS 270. Very easy, very fast. And then two of those, the 2 CIS 0 is 2, equal to 2. 2 CIS 180 is equal to negative 2. And the other ones, 2 CIS 90 is actually just 2 times I. And then 2 CIS 270 is just minus 2I. So you get, again, evenly spaced roots. And that just takes a little bit more practice to do that. But again, the steps for doing that, I think, are pretty straightforward. You write your number as a polar form complex number. I like to do RCIS theta. Find R, find theta. Then raise that number to the 1 over n power. Use DeMoivre's theorem to quickly simplify. Then after we do that, we simply repeatedly add 360 over n. Or if you're in radian mode, you could do 2 pi over n to find all those other ones. So hopefully you found this helpful. Happy studying for that test that you got coming up soon. And see you guys all in class. If you have any questions or comments, feel free to email me or write it in the comment board. Have a great day.